you, folks. You spin me right round, baby, right round, like a record, baby, right round, round, round. You spin me right. I don't even know if you could hear my thing. Super loud. Nobody's home right now. Okay. Let's get out of here. All right. Woo! I haven't played any music in a while, and I was putting together these slides on rotations and particle on a ring, our next problem, and I couldn't get that song out of my head. You spin me right round, baby, right round. Okay, anyways, so obviously you can tell what we're getting into. Particle on a ring. Let's go, let's do it. So there's going to be a lot of things that we build from classical mechanics in describing the rotations of particles in terms of quantum mechanics. Okay, so the first thing I'm going to set up is our physical picture, this particle on a ring. Okay, and on this picture we have, notice our scale here, Z, X, and Y. We're going to be giving special attention to the Z-axis in this discussion because we have to choose one axis. As it turns out, there's going to be a little Heisenberg uncertainty principle going on. So we choose the Z-axis arbitrarily. Okay, so it doesn't matter. We've picked Z. So our particle is spinning around in this plane that goes in and out of X and Y. So it's rotating in the XY plane. Okay. So for now, we're going to say there's a 0 potential energy in that plane. So we only have to deal with kinetic energy. You can see now we've got the mass of the particle, radius to some center point. And then, of course, we have its linear momentum given by P. Okay. And, of course, its angular momentum given by J sub Z. So Z for the Z-axis. So you can see my lovely picture here reminding you of the right-hand rule and the cross product. So that X right there, right, that's the cross product, P cross R, okay? So if you look at here, the way this is notated, the A and B vectors, okay? So I always have to kind of think about this for a second. Yes, so A, my pointer finger, that's gonna represent the linear momentum. Okay, notice that it's tangential to the radius. And so then my middle finger is the radius. And if I rotate as the picture is showing, my thumb points in the direction of the angular momentum. Okay? So you notice here that angular momentum is plus or minus P cross R. And it's plus or minus because now, right, if I want to start spinning in the other direction, my angular momentum, right, is now pointing in the opposite direction. It's pointing towards the negative Z. Okay? Excuse me. Okay, so continuing along. We know kinetic energy is P squared divided by 2m. That's something we've talked about quite a bit, right? That comes from 1/2 mv squared. We know, we've just talked about that angular momentum is plus or minus P cross R. And then also we're going to take advantage of the moment of inertia, I equals mr squared. Okay, so this is all from classical mechanics, and this is helping to build our picture so that we can build up an operator and then eventually solve a Schrodinger equation for this problem. Okay. So let's see. I think I've talked about everything I wanted to on the slide. So let's keep going. So continuing along. Okay, so putting together our equations here, still dealing with this classical mechanics world. So we know that if the kinetic energy is P squared divided by 2m, and we're only dealing with kinetic energy, right? There's zero potential energy. Then I can rewrite my energy, kinetic or total, right? It's the same. I can write that as the following. So I recognize that the momentum squared, I can write that as jz squared divided by r squared. Okay, so I substitute that result in, and I get the following. So the energy is going to now equal the angular momentum squared divided by 2 mr squared, and we know mr squared is moment of inertia. So we're going to see this as our kinetic energy for this particle on a ring, jz squared divided by 2I. And we should keep in mind that this is still all classical. We haven't put any quantum stuff on this, right? This is just a particle spinning right round, baby, right round. Let's add the quantum touch to that, okay? And so the quantum touch that we're going to add is the de Broglie wavelength. So we remember now that in the quantum world, momentum is h divided by lambda, where lambda is the wavelength of our particle. It's the associated wavelength of the particle, which has wave-particle duality. So let's smash these equations together, okay? Oh, excuse me, not yet. First, we have to talk about how to quantize this, how to make this acceptable for quantum mechanics. So we have what's called out-of-phase rotation and in-phase rotation. So if I look at the out-of-phase rotation, okay, so for example, suppose on my first circuit, right? So imagine I'm taking my particle right round, baby, right round. We're spinning it around. So what I've got here now, this is the particle's circuit, but plotted linearly, like spread out on a linear graph, okay, given by the radians, right? 0, pi, 2 pi for a full complete circuit, right? 2 pi for a full circuit, okay? So if I start at 0 and I end up here, you know, halfway, that's pi. And then if I go around the other half, right, I get to 2 pi. Okay. So on this quantization, if let's say I start here on the first circuit and I'm going through this first circuit and I'm going, you know, as a wave through this circuit right here, and I finish my 2 pi full loop circuit down here. Well, then look where I start the next circuit, right? I go all the way up and I start the second circuit right here. Well, you can see right away that's going to be problematic because my Schrodinger, my wave function has to be single valued. And so as I go and make successive loops, successive circuits, you can see that it's not single valued, right? It's a double valued function. So that's what we call out of phase rotation. So what we have to do instead, we have to have in-phase rotation, where if I start up here and go through my first full circuit from 0 to 2 pi, I have to end up where I started. Because now when this goes to its next loop, it's gonna be single valued, okay? So this is our main boundary condition requirement in the particle on a ring problem, is we have to have in-phase rotation. So due to the requirements of acceptable solutions to Schrodinger, only certain Jz values are acceptable. So in other words, to maintain this in-phase rotation, it's really going to be all about the angular momentum. We're going to fix the angular momentum to give us that in-phase rotation, okay? So here's what happens. So we've got our classical mechanics equations, we've got our quantum mechanics equations. Let's smash them all together. So we know, we can write here that classically Jz is plus or minus PR. I'm just going to write that as PR, even though we know that it's technically the cross product, okay? And I know here the de Broglie wavelength, that P equals H divided by lambda. So now that's a pretty obvious place that I can combine these. So I can say Jz equals plus or minus HR divided by lambda, okay? And again, plus or minus because, right, I can be rotating in this orientation or I rotate in this orientation, okay? So what is the wavelength for this thing? Well, the wavelength here is we're going to ascribe this closed loop or in phase motion. And to get that, what we're going to say is then the wavelength has to be some integer value of the radius. And that integer we're going to use, it's not an integer, rather it's a trigonometric function, 2 pi r, okay, to give us that 2 pi full loop. And then this is going to be divided by a new quantum number that will give us quantized in phase motion. So now we have no idea what letter to use yet, so we're going to foreshadow, and we're going to call the new quantum number m sub l, ml. That, in fact, is the ml that you know and love. That is called the magnetic quantum number, okay? And it can take on the following values. So for now, we're going to pretend that we don't know what values ml can actually take on. So when we try to figure out how we're going to do this closed loop motion, we recognize, well, it's got to be in these, integers of 2 pi or these circuits of 2 pi. So what that means is plus or minus 1 is okay. And again, the plus or minus for the, the change in angular momentum. It means that plus or minus 2 is okay as well. And as we shall see, we're going to be able to add other qualifiers to this ML. As it turns out, plus or minus 1 and plus or minus 2 aren't the only values that are acceptable. But for now, this is as much as we can say that is acceptable for this quantum number. Okay, so I think, let's see, I might have a picture of that coming up. But so now if we keep going with this and we recognize that Jz equals plus or minus HR over lambda, and then we substitute our quantized solution for lambda, then what we get is plus minus ml h times r divided by 2 pi times r. And all of that is going to equal plus or minus ml times h bar. So the radius and the radius cancels, and we know h divided by 2 pi is h bar. Okay? So what we see classically, let's see, I think I have that on the next slide. Yes. So we can see now that the energy associated with this particle rotating classically can be written as Jz squared divided by 2i. Okay? But as far as where quantum is concerned, right, we wrote that Jz is mlh bar. So that means when we substitute that mlh bar in for Jz, we get that in terms of quantum mechanics, E is ml squared, h bar squared divided by 2i, okay, where Jz equals mlh bar. Now, I only showed you that plus minus 1, plus minus 2 are what we think are acceptable so far. We're going to see later on, coming up shortly, that 0 is acceptable and that 3 is also acceptable, okay? We're going to see how that manifests. And what's also important to note that the plus minus, that means that these ML states are in fact doubly degenerate. So the ML plus 1 has the same energy as ML minus 1. They're opposite in sign, right? We recognize, if it was 1, E then would be just h bar squared divided by 2i. But if it was a minus 1, it would be minus h bar squared divided by 2i. But those are degenerate because that negative sign, again, it just describes the different orientation, whether it's rotating this way or whether it's rotating this way. Okay? So now our next step is to determine if this is acceptable to the Schrodinger equation. Because we've kind of done this in sort of a backwards different way than some of our other problems. I mean, look, we already have a solution to the energy without even putting together a Schrodinger equation. We already have a quantized solution for energy. So we have to test if this is going to work for the Schrodinger equation. Okay? So let's get it set up. So there's a couple things we've got to do. We're going to have to do a coordinate transformation, because to describe this rotation, spherical coordinates is going to be the most straightforward. Okay? And so for now, we also recognize, because this is particle on a ring, our particle is only moving in the xy plane. So when I start to build up my Hamiltonian, right, for kinetic energy, because again, V equals 0, so we're only worried about kinetic energy. So that's negative h bar squared divided by 2m times the partial second derivative in x plus the partial second derivative in y. And this is the exact same thing that we did with the two-dimensional particle in a box. So here, this thing that I've got, this upside down triangle, so that's called del squared. Sometimes it's also called nabla. And sometimes it's also called the Laplacian. So all of these are names to describe this operator. And this operator is the partial second derivatives in multi-dimensions. And so we can have the two-dimensional del squared, or we can even have the three-dimensional del squared that would include the plus z dimension. Okay? So we're going to get used to seeing this. I like to refer to it as del squared. But again, nabla, Laplacian, del are all appropriate names for that operator. Okay? So now this is where this does get a bit nasty at first. As you see where this is going, because we need to transform our xy space into r theta phi space. So for now, this is not so bad at all, because for one, r is constant. Okay, so we're just going to allow for one single radius. We're not going to allow for the particle to move in and out of the origin. We're just going to say it's fixed at one radius, spinning right round, baby, right round. Okay, and we're also going to be ignoring theta. So we'll say theta, we're not going to worry about it, right? Because remember, theta goes in this dimension. We'll eventually have to think about the theta dimension when we turn this into particle on a sphere. But for now, the only thing that we actually care about is the partial in phi. And here's why, okay? So through standard manipulation using these relationships, that the sine of phi is r divided by y, and the cosine of phi is x divided by r. So this is from SOHCAHTOA, right? Then the two-dimensional del squared, right, in x and y, that becomes the second derivative in r squared plus 1 over r times the first derivative partial in r plus 1 over r squared times second derivative in phi. So I'm not going to hold you responsible for doing that manipulation because it is a standard coordinate transformation. And it at first looks like really nasty, right? Like, what are we going to do with all these things? However, because r is constant, we don't care about any of the derivatives of r. Okay? So this goes away. And this goes away. Which means also that 1 over r term that's in front of that derivative goes away because the derivative is 0, given that r is constant. Okay? So now, look, this is the only thing that we have to worry about for our Laplacian, or for del. Okay? So now, check this out. Our kinetic energy Hamiltonian operator, right, becomes negative h bar squared divided by 2m. So there's still that part. But now we just replace it with the 1 over r squared partial second derivative in phi, which I get right here. And look how sweet and easy that becomes, right? We know mr squared is just moment of inertia I. And I replace the partials with d's because now we only have one single dimension to deal with, okay? And it looks exactly like our kinetic energy operator for translational motion, which is great. Okay, so continuing along with this thing. Let me check the time. Okay, 20 minutes. We're doing great. So now my Schrodinger equation, h psi equals e psi, becomes very simple. So my operator now is just negative h bar squared divided by 2i times partial derivative, second derivative in psi equals e psi, okay? So let's do this thing. We can solve this all day long. Cry, pray, guess, solve. We can do this. And that's what we're going to do right now. So let's go for it, okay? So here I have my Schrodinger equation. And the first thing that I want to do is get that in the standard reduced form, okay? So I'm going to just do that algebra right here, right? I'm going to multiply negative 2i over h bar squared through. Okay, so I get second derivative in phi of psi. And now that equals negative 2ie over h bar squared times psi. Okay, and putting that into our standard form, where I set the right side equal to 0, that becomes plus 2ie over h bar squared times psi equals 0. This is a very easy, straightforward second order differential equation to solve. Okay, we're going to guess, right, that psi equals e to the a phi. I know it's tempting to say e to the ax, but remember phi is our variable. And so now I'll just go very quickly to the second derivative directly, right? We know that that's going to be a squared e to the a phi. So this is all looking very familiar and all good. And so then when I plug that into this whole thing, right, I get now a squared e a phi plus 2ie divided by h bar squared. And then now times psi, which we guessed is e to the a phi, all equals 0. So we know that we can eliminate the e to the a phi. And so that's going to give me a squared plus 2ie divided by h bar squared, all equals 0. And I think you can see where this is going. We're going to get imaginary roots, right? So this is going to be now a equals negative 2ie divided by h bar squared, all square root. And so now I'm going to use some other foreshadowing here. I'm going to use a different letter than a, okay? So, excuse me, I'm going to say now that a equals I times m sub l. Why am I going to use m sub l? Well, because actually, as it turns out, look at this. This is really cool. So now we know that this ml right here, okay, equals the square root of 2ie divided by h bar squared. So how did I know to use that ml? Well, let's back up for 1 second. Aha! Right? E equals ml squared times h bar squared divided by 2i. Well, what if I rearrange this? Let's do that. So I multiplied both sides by 2i. So I've got 2ie. And now I'm going to divide both sides by h bar squared and take the square root. That gives me quantum number ml, which is really, really cool that we know that it's a quantum number. It's got to take on only integer values that we've seen, plus minus 1, plus minus 2. But the fact that it's also equal to the square root of 2 times the moment of inertia times the energy divided by h bar squared, all square root, and that this, in fact, will equal plus or minus 1, plus or minus 2, etc. That's pretty cool, I think. Okay. And so now when we go, let's see what's coming next. Oh, I've got a whole nother slide. So now we can say that psi of phi, so we know that this is imaginary roots. So that means it's going to be a, some normalization constant, e to the I ml phi, plus b e to the negative I ml phi. All right. And so now what we're also going to look at here, because we recognize that ml can already be plus or minus, we technically can just write this as psi equals a e I ml phi. Again, because we already know that ml can already be plus or minus. All right. And so now, let's see, when we go to normalize this thing, it's pretty straightforward, okay? So we're going to normalize it as psi star psi, right? So that's going to be n squared over, so we don't need to worry about the theta or the r. They're gone, right? So we're just going to go from 0 to 2 pi. So I'm replacing my a with my n squared, right? And now we have to remember, because that's got an I in it, my psi star is negative ml phi. So that's really important. So I have to consider that conjugate now, right? Because we're dealing with i's. So now when I go to plug these in, right, it's going to be ei ml phi, so negative, I'll do the conjugate first, times ei ml phi, d phi, and that all has to equal 1. Well, check out what's going to happen. So these two things eliminate each other, right? It just becomes 1. And so now I've got n squared from 0 to 2 pi of d phi equals 1. And so we know that then the integral from 0 to 2 pi of d phi is just 2 pi, okay? So now that's 2 pi times n squared equals 1. And so we can see finally n, the normalization constant, very simple, is just going to be 1 over square root of 2 pi, okay? So what does this mean now? Well, what this means, for one, if we look at our wave function, I'm going to write the wave function as psi of phi equals 1 over the square root of 2 pi e to the I ml phi. And so what about this ml? Can we get those quantum numbers that we talked about out of this ml in a different way? Okay? And so what we can do is we have to recognize for this closed loop motion, okay, psi of, so I'm going to write this up here. So psi of phi must equal psi of phi plus 2 pi, right? So in other words, the value of psi at phi, when it comes around and makes a full 2 pi loop, those two values have to be equal to each other, okay? So that means that now, so I've got this psi of phi, but now if I write psi of phi plus 2 pi, so that's going to be 1 over root 2 pi e to the I ml times phi plus 2 pi. And what do we get out of this thing? Well, for one, let's see here. We know that we can do some algebra on this. And I can write this as 1 over root 2 pi times e to the I ml phi times e to the 2 pi times I ml. So I just did some algebra there, right? Separating the exponents, okay? And so I think I probably didn't leave myself enough room. So then I'm going to write another proof here that we're going to use. So recall, I call this the God Theorem. E to the I pi actually equals -1, which is really cool. And so you can see that we have that. I've got an e to the 2 pi I, okay? So I can rewrite that as the following. Man, oh man, I wish I left myself more room. So let's see here. Okay, I'm going to add a slide. Nope, I didn't want to do that. I'm going to add a slide at the end. Okay, so yes, so I'll just rewrite this again. Sorry, psi of phi plus 2 pi equals 1 over root of 2 pi e to the I ml phi times e to the 2 pi I ml. Yep, I got that. Okay. And we know that e to the I pi equals -1. So now I can rewrite this as the following. And so also, I'm going to note that psi of phi equals 1 over root 2 pi e to the I ml phi. Okay, great. So now when I rewrite this, check it out. I've got a 1 over root 2 pi e to the I ml phi. So this chunk right here just becomes psi of phi. Brilliant. So, but now I've got an e to the I pi, and I'm going to write that as -1, but then it's still raised to the 2 ml power. Okay. So now, if I continue along here, and I recognize that my psi of phi plus 2 pi has to equal also psi of phi. So remember that boundary condition. Psi of phi has to equal psi of phi plus 2 pi. So now instead of writing this as psi of phi plus 2 pi, I can just write this as psi of phi. And then now what I'm left with, I can cancel the psi of phi and write that because it comes 1 and 1. And so now I get 1 equals 1 times -1 raised to the 2 ml power. So what are the values that ml can take? Well, anything raised to the 0 power is 1, right? So if I take 1 negative, just to prove this, okay, and I raise it to the 0 power, I get +1. So that means ML0 is possible, okay? Well, what if this was, ML was +1, let's say, okay? Then -1 raised to the, 2 times 1 is 2, so -1 squared is 1, so that checks out, okay? But what if this was -1 raised to the -2 power? I'm going to do this just to prove that it works. -1 raised to the -2 power is still +1. So plus minus 1 works. What about plus or minus 2? I mean, let's try it, right? What's -1 raised to the 4th power? It's +1. Brilliant. And as we will find out, we can just keep going on and on and on with this, etc. And all of these ML values are possible, which is sweet. So in more than one way, we came up with this quantum number ML, solving the particle on a ring problem, okay? And the last thing where I will leave off for this lecture, I'm going to go back to where we came. Okay, so where is the damn particle on this ring anyways? Can we say with arbitrary precision where it is? So we know this is the wave function, 1 over 2 pi e to the I ml phi. Great. So this particle on a ring is going to look something like this, right? Where it's oscillating around. And if I drew this correctly, then I'll have a closed loop motion. Yeah, great. Something like that. Okay. So where is the particle? Well, remember, if I take psi squared, and here specifically I'm showing you the square modulus, because once again, we have imaginary numbers in our wave function, right? Well, the square modulus of this function just gives us 1 over the square root of 2 pi. So what is the manifestation? Well, probability density is independent of angle phi. Look, there's no phi dependence on psi squared. It's just a constant. So that means the probability of finding the particle somewhere on the ring is indefinite. It's on the ring, but we don't know where it is on the ring because we didn't get a phi dependence. So the fact that the square modulus is just coming out 1 over square root of 2 pi, it just tells us the particle is somewhere on that ring. Okay? So precise knowledge of the angular momentum will actually eliminate the possibility of precisely knowing where the particle is located. So in other words, now, if instead of trying to figure out where the particle is on the ring, let's suppose instead we really try to precisely know its angular momentum. Okay? Well, if we were to do that, we would then find that angular momentum and angle, so jz and phi, make a set of complementary observables that are suspect to Heisenberg's uncertainty principle. And we're gonna have to deal with that next. Okay, folks, I'll see you on the next one.